Okay. All right, everybody. I hope you got the chance to get acquainted with your groups. We're going to go ahead and start with class. So great. I hope you got a chance to exchange contact info. You can decide how you want to communicate with your groups. If you need any kind of service provided by me to facilitate discussions through your groups, let me know. I think in the past, most groups have just taken care of this by themselves. So you can use whatever communication protocol you think works best for you. Note that the seats you are sitting in now, those will be the exact seats that will be used to take attendance. So I moved a couple of you slightly to the left. Note that if you need to be sitting in the assigned seat in order to be counted present. So just make sure you're sitting in your correct seat. For every row except the first row, there will be one blank row at the edge. Okay. Also, to clarify, Becky will be taking attendance at the very beginning of class. Okay. So if you aren't in your seat at the beginning of class, you will not be marked present. Now note there may be a little bit of tolerance if you come in when she's taking attendance, but note that if you come in after 3:30, there's no guarantee that you'll be counted present. Okay. Okay. Are there any questions on seating and attendance? Any questions? Okay. And as I said before, if you have any issues with where you're sitting or with your groups that you still need to raise with me, please do so by today so I can get those figured out. Okay. All right. Awesome. Okay. So let's go ahead and get started. We got another action-packed lecture for you today. A couple of quick announcements before we get started. Project groups and seating charts are posted, obviously. Second, I decided to extend homework 1 until Tuesday because we didn't get through discharge control structures yet. We'll be getting to that today. But please go ahead and be proactive about that homework assignment. It may be a bit longer than you were thinking. So I would like to see some people in office hours asking questions. I haven't gotten anybody in office hours yet asking questions, which is, you know, those office hours are there for you, for your benefit. So please come in if you have questions. Okay, great. So homework 1 will be due Tuesday. All right, so let's go ahead and get started. Quickly reviewing what we covered last time. Last time we introduced the energy equation. We showed how it could be derived from our St. Venant equations for unsteady flow in open channels. We talked about sub and supercritical flow, as well as critical flow. We showed the definition of critical flow and where it comes from, and we introduced Froude number, which you may remember from hydraulics, is used to characterize, you know, what flow regime you have, whether it's critical, super, or subcritical. And finally, I introduced and solved a mystery problem involving channel transitions, okay, which we're going to revisit today. Today, we are going to finish our module on open channel flow. So this is our last lecture on open channel flow before we move on. We'll be revisiting the channel transition problem that I introduced last time. We're going to be discussing what critical flow really means. Okay, we're going to be taking kind of a broader look at what critical flow means and kind of look at it more conceptually as opposed to just looking at the math. And finally, we're going to introduce discharge control structures, which will be important for the rest of the course, namely orifices and weirs, which you had some experience with in hydraulics, but which you will also need for the first homework assignment. Okay, great. Are there any questions on course logistics or the material before I move on? Any questions? All right. So let's go back to the problem that we discussed in last class. This is a channel transition problem, which involves the use of the energy equation. And at the beginning of class last time, I gave you this mystery scenario. Okay, so we have flow in an open channel. This is a horizontal channel, and the bottom of the channel undergoes a smooth transition in the bottom elevation. Okay, so we start with some initial elevation, and it transitions to a height of delta zeta naught. And my question to you was, what happens when the flow encounters this bottom transition? Okay, does it go up? Does it go down? Or does it stay the same? And we took a vote for what the answer is. And I believe most of you believe that the depth of the flow would remain the same, that the water surface elevation will remain the same. Okay, so we showed that we could solve this problem by applying the energy equation as well as the continuity equation. And I went through this procedure at the end of class, but I didn't finish it. So let's go ahead and just revisit our solution procedure from last time. Okay, so first we computed the flow within this channel by essentially multiplying the velocity at the upstream end by the depth and the width of the channel. Okay, so we know that the flow at the upstream end Q1 has to equal the flow at the bump Q2, which we'll just call Q. And this was equal to U1 H1B, which ended up being 27 cubic meters per second. Let me just add some numbers here. Our velocity U1 was 3 meters per second. The depth of flow at the upstream end was 3 meters. And this channel bottom bump, this was 0.3 meters. Okay, so we showed that the discharge within the channel was 27 cubic meters per second, and that discharge was the same at the upstream point as well as at the bump due to continuity. Okay, the next thing we did was we applied the energy equation between these 2 points. So this is point 1, this is point 2. And applying the energy equation, we have that the depth at point 1 plus the velocity at point 1 squared over 2g is equal to the depth at point 2 plus the velocity squared over 2g at point 2 plus delta zeta naught. Okay, so this is just an application of the energy equation to this open channel flow problem. And when we plugged in values and we rearranged the problem, what we eventually got was the following cubic polynomial, which I'm going to write on the next page here. That cubic polynomial was solved to determine the depth, H2. Okay, so our cubic polynomial is in H2. It is H2 cubed minus 3.1587 times H2 squared plus 4.1284 is equal to 0. Okay, and we showed that we could solve this. Okay, so we solved using a computer. And we found that the roots of this equation are the following. Okay, so the roots ended up being 2.496, 1.659, and negative 0.997. Okay, so H2 has to be one of these 3 options. Okay, so right away we can discard the negative root because it's non-physical. And the remaining problem was to determine which of these 2 other roots correspond to the actual depth H2. Okay, and I told you that this root here corresponds to H2 being subcritical. And this root here corresponds to H2 being supercritical. Okay. And last time I spoiled the answer for you, and I told you that it was the subcritical root. Okay, but I haven't explained why that's the case yet. To answer that question, we have to examine essentially how the flow regime changes as you move along the specific energy diagram, okay, which is what I am going to show you now. Okay, I'm going to show you why this root is the correct answer. Okay, are there any questions before I move on? Yes. Okay. Okay, so before we can figure out what the depth is at H2, we need to know what the flow regime is at the upstream end, okay? So how can we compute, how can we determine whether the flow at the upstream end is critical, supercritical, or subcritical? Yes. Right, we can look at the Froude number at the upstream end. Okay, so the Froude number at the upstream end, we can go back to our definition of the Froude number. Okay, and we know that this is equal to the velocity at the upstream end times the square root of the top width at the upstream end divided by the square root of the acceleration due to gravity times the area at the upstream end. Okay. Now note that this is a rectangular channel. So the top width is equal to the bottom width, and that will just be equal to B. Okay. B is the bottom width, and that's equal to 3 meters in this case. And similarly on the bottom, we can express the cross-sectional area as B times H1, which is known. Okay, and if we substitute in our known values, we get 3 times the square root of 3 divided by the square root of 9.81 times 3 times 3. Okay, and when we evaluate this, we get 0.553. Okay, so is this subcritical, supercritical, or critical? Right, this is subcritical. Why is it subcritical? Right, the Froude number is less than 1, and therefore the flow at the upstream end is subcritical. Okay. So with that said, let's take a look at the specific energy diagram and how the water profile moves along that specific energy diagram for this problem. Okay, so I'm going to draw out the channel as well as the specific energy diagram for this problem. Okay, so we have the channel bottom. And on the right here, I'm going to draw our specific energy diagram. Okay. And we have flow in our channel. The depth at the upstream end is H1, velocity U1. We have some depth at the bump H2, some velocity U2. Okay. This here on the right, this is our specific energy diagram. So the y-axis is our depth, H, and the x-axis is our specific energy, which is equal to H plus U squared over 2G. Okay, so let me go ahead and draw a diagonal line here. And we have our specific energy curve, which will look something like this, right? Okay, so what happens when we apply the energy equation to this channel? What we get is the following expression. We have H1 plus U1 squared over 2G is equal to H2 plus U2 squared over 2G plus delta zeta naught, right? Let's take a look at each of these terms. So what is this term right here equal to? Okay. What is this term equal to in terms of this diagram here? Yes.
The specific energy at that point.
Right. So this is the specific energy at the upstream end, right? Which means that this here is the specific energy at the bump. Okay, so we get that E1 is equal to E2 plus delta zeta naught, or equivalently, E2 is equal to E1 minus delta zeta naught. Okay, so how does E2 relate to E1? Which one is larger? Which one is larger? E1 is larger, okay? So the specific energy at point 2 is less than the specific energy at point 1, and that just comes from applying the energy equation, okay? So let's look at how that corresponds to our specific energy diagram. Okay, so this line here, let's say this is E1, and let's say we have another line here, E2. Okay, and so for E1, that corresponds to 2 alternative depths. Okay, it lands at a point A on the specific energy curve up here in the subcritical regime, and another point A prime here in the supercritical regime. Okay, so this corresponds to a subcritical depth. This corresponds to a supercritical depth. Okay, for E2, we also have 2 points on the specific energy curve. This is point B up in the subcritical regime and B prime in the supercritical regime. Okay, so when the flow encounters a bump in the bottom, our specific energy decreases from E1 to E2, right? So this distance here on the specific energy curve is exactly equal to delta zeta naught, right? Because E2 is equal to E1 minus the height of the bottom transition, right? Okay. So what happens when we are up here in the subcritical regime? Okay. When we encounter the bottom bump, we move along the specific energy curve from A to B, right? And the depth decreases from H1 to H2, right? So if we start subcritical, is it possible to end up at the supercritical point at the crest of the bump? If we start at the subcritical H1, is it possible to move along this curve and end up at the supercritical H2? Is that possible? I see some shaking of heads. I see some shaking of heads. Does anyone want to venture a guess whether it is possible or not possible for it to end up at the supercritical? Right. So what would it take to arrive at the critical point? Sorry? So we're going from subcritical to supercritical. So a hydraulic jump would occur the other way. Why isn't it possible to move from this point A to this point B prime? Yes. So we're moving along this specific energy curve. If you got to the critical depth, right, what would that mean in terms of the bottom, the raise on the bottom elevation? So yeah, you would have to move to you would have to have a larger increase in the bottom elevation of the channel, right? So we'll call this delta zeta max. Okay, this is the largest rise in the bottom elevation of the channel that can be accommodated for this flow, right? When you arrive at this delta zeta max, that means that you have achieved critical flow at the crest of the bump, okay? Why can't we move from A to B prime in this problem? Yeah, exactly. We don't have a large enough bump, right? To move from A to B prime here, you would need to move through a larger bump before the crest of the bump, right? Which doesn't correspond to our problem statement, okay? So that's why the depth at the crest of the bump has to be the subcritical depth, which is why our answer has to be 2.496, okay? Yes.
At what point would you want to
Well, it could happen if you didn't encounter a bump at all. It could also happen if somehow you had a scenario where you went from A through the critical depth and all the way back to A prime. Then you would have the same specific energy, but they would be at the alternative depths. So it is possible for E1 to equal E2. Okay, great. So in summary, we have that our mystery, the answer to our mystery is that H2 is equal to 2.496 meters. And the water surface elevation is equal to H2 plus delta zeta naught, okay, which is equal to 2.796. Okay, so for this case, when the water encountered the bump in the bottom of the channel, the water surface actually decreased as it moved over the transition in bottom elevation, okay? But the mystery I gave you was actually a trick question, okay? As some of you guessed, right? Because it depends on what? Exactly. It depends on the type of flow at the upstream end, whether it's critical, subcritical, or supercritical. What would happen if the flow coming at the upstream end was supercritical? Would it go up? Would the water surface elevation go up, or would it go down? Right. The flow on the specific energy diagram, we would move from this point here, A prime, which is in the supercritical side, and we would move to B prime, which would result in an increase of the depth of the water. Okay, so in summary, it was a trick question. It depends on what your flow regime is at the upstream end of the channel. Okay, so keep in mind when you're doing your homework problems to keep this idea in mind. Okay, great. Are there any questions before I move on the channel transition problem? There is a channel transition problem on the homework, just a different sort of channel transition problem. Okay, any questions before I move on? Yes.
So I guess, so after that bump, would it also just like return to its original water level?
Yes. So assuming that there's no dissipation of energy and it doesn't go through the critical depth, it will end up back at its original depth. Yes. Which takes me into the next subject I wanted to get into. Are there any other questions before I move on, though? Any other questions? Okay, so I'm going to give you a quick example problem to work on with your groups. We're going to be looking at the same scenario. Okay, so for the same scenario, as in the previous problem, we want to design the bottom ridge. Okay, we want to design the height of the bottom ridge such that critical flow occurs at the crest of the ridge. Okay, so I want you to find the value of delta zeta naught to ensure that critical flow happens at the crest of that bump. Okay, and I will just write down the parameters from the previous problem. Okay, we have that the bottom width of our rectangular channel is equal to 3 meters. We have that the velocity at the upstream end is equal to 3 meters per second. And we have that the height, or the depth of the water at the upstream end is equal to 3 meters per second. 3 meters. Okay. So I'm going to give you about 5 minutes to work with your groups to solve this problem, and I will check back in and see what you got. Okay. Great, and flag me down if you have any questions. Okay. Okay. So in the interest of time, I will go ahead and reveal the answer. Okay, so we want to find the transition in the bottom elevation that causes critical flow to occur at the peak of the bump. So what's the first step that you took when trying to solve this problem? Right, so that's kind of the natural place to start for this problem, is to set the Freud number equal to 1 and determine the critical depth that has to occur at that bump, right? Okay, so we can do that. I am going to write it in terms of the Freud number squared, which is still equal to 1, which is equal to Q squared times the top width over GA cubed. Okay, so I'm going to just rearrange this. We rearrange it, we get Q squared. T is equal to B because it's a rectangular channel. So T is equal to B, and A cubed is equal to B cubed times the critical depth cubed, right? Okay, so if we rearrange this, we get Q squared B is equal to G times B cubed times the critical depth cubed. Okay, and we can just rearrange for the critical depth. We get that the critical depth is equal to the cube root of Q squared divided by G times B squared. Okay, and if we substitute in our numbers, we get that this is 27 squared over 9.81 times 3 squared. Okay, and the critical depth that you should arrive at is 2.021. So I saw that several of you got this answer. So what's the next step that we need to take in order to determine the change in the bottom elevation needed to attain the critical depth? What other equation can we use here? Energy equation. Okay, so let's apply the energy equation at both of these points. We have that H1 plus U1 squared over 2G is equal to the critical depth plus Q squared over 2G B squared HC squared, so HC is the critical depth, plus delta zeta naught. Okay, and we have every variable here except for delta zeta naught. So we can solve for delta zeta naught. If we plug in the values for these expressions, we get 3 plus 3 squared over 2 times 9.81 is equal to 2.021 plus 27 squared divided by 2 times 9.81 times 3 squared times 2.021 squared. I'm going to put these in parentheses to make it easier to read. Plus our value for delta zeta naught. And solving for this value, you should get a value of 0.427 meters. Okay. So are there any questions on this before I move on? I noticed that several of you did this procedure but got slightly different answers. So please double check both the work I've done here as well as your own work and just check it. But essentially the solution procedure involves determining the critical depth and then applying the energy equation between the 2 points. Okay. Are there any questions and or comments before I move on? Yes. The first equation, this one. So this is the expression we derived when we were deriving the condition for critical flow, and it's equivalent to the Freud number squared. So if the Freud number is equal to 1, the Freud number squared is equal to 1, and you can solve for the critical depth using this condition. Yes. Oh, so yes. No, sorry, I used Q. Yeah, Q has to be 27 cubic meters per second. You can compute it at the upstream end. And because of continuity, it has to be the same flow at the bump. Okay. So the flow at the upstream end has to equal the flow at the bump, or else what would happen? Right. If the flow were different between the 2 points, then you would end up with water accumulating somewhere in the system, which would result in it changing over time. Okay. All right. Okay. So are there any questions on this problem before I move on? Any last questions? Okay. So the next question I want to ask, let's just talk a little bit about sub, super, and critical flow. Okay. What are some conditions that characterize subcritical flow? What does it mean if flow is subcritical? Okay, so for subcritical flow, it's slower. What else? What mathematically, what characterizes subcritical flow? Yes. So often larger cross-sectional area. Okay. Okay, and what about supercritical flow? What characterizes supercritical flow? What's kind of the way that we characterize supercritical flow? What's kind of the definition that we use? Okay, so it's fast, shallow. Okay, so in terms of the definitions that I gave you previously, if we look at the Freud number, for instance, subcritical flow occurs when the ratio of inertial to gravitational forces is less than 1. So in other words, when a majority of the specific energy is in the potential energy component, and supercritical flow occurs when the majority of the energy is in the inertial component, or the component due to velocity. But there's perhaps a more intuitive way we can think about supercritical, subcritical, and critical flow. Here's a question I have for you. Is it possible to tell if flow is subcritical, supercritical, or critical just by looking at it? Who thinks that it's not possible? Okay, so some of you. Who thinks that it's possible? Okay, why is it possible? Can we tell if flow is supercritical, subcritical, or critical just by looking at it? Yes. Okay, is there a way we can tell exactly? There actually is. Okay, and so what I'm going to show you in this next section is another way of thinking about critical flow and what critical flow really means. Okay, and what I'm going to show you is that critical flow is characterized by the condition that the velocity of the water is exactly the same as the velocity of a wave traveling in that water. Okay, so that is what intuitively characterizes critical flow. Okay, so in this next section, what I'm going to show you, okay, in critical flow, the velocity of the water is exactly the same as the velocity of a disturbance wave. And the consequence of this that I'm going to show you is that you can tell that flow is critical or supercritical or subcritical just by looking at waves as they move through that water. Okay. This also has important implications for design because it affects, essentially whether changes in the stream, essentially whether changes imposed by controls can propagate upstream. Okay. Okay. So let's consider water in a quiescent channel. Okay, so we have a channel in which the water is still, it's not moving. So we have our bottom of the channel here. We have some water surface elevation here. Okay, so this water is otherwise still. It has a depth here of h and a velocity of u. Actually, I'll call this u bar. Sorry, no velocity. It's still, as I just said. And let's say that a disturbance occurs in the water. So let's say someone comes over and throws a rock in the water, and it causes a ripple to occur in the water surface here. Okay. So we'll call this a small gravity wave for reasons that will become apparent. So we have still water, and we have someone came over and threw a rock into the water, and it caused a ripple to occur in the surface of the water. And let's say that this ripple is moving to the left with a wave speed of c. Okay, so this wave is moving to the left with a speed of c. Okay. Now, let's go ahead and just align our frame of reference with the moving wave. Okay, so we are looking at the wave and we are moving alongside the wave with our frame of reference, tracking the wave. Okay, so the wave is actually moving to the left with a speed of c, but from our perspective, if we align ourselves with the wave, it appears as if the water is moving to the right with a velocity of u bar. Okay, so the water is still, the wave is moving to the left with a speed of c, but if we align our frame of reference with the wave, the water will appear to be moving to the right with a velocity of u bar. And mathematically, the two are equivalent. This will just simplify the math for the rest of this section, okay? Okay, so over in this section of the channel, we have a depth of h, a apparent velocity of u bar. And at the location where the wave is occurring, we have a depth of h plus delta h and a velocity of u plus delta u bar, okay? So essentially by continuity, because the depth changed at this point in the channel, the velocity also has to change to satisfy continuity from this location to this location. Okay, and I'm just gonna call this location 1 and this location 2. Okay, so let's go ahead and analyze this problem a little bit. Let's first just apply continuity between the two sections. Okay, and so by continuity, we know that the discharge, the apparent discharge at this upstream end has to equal the discharge at the wave. Okay, so we can write this out. Let's also just assume that we have a rectangular channel with a width of b. Okay, so it's a rectangular channel with a width of b, which means we can apply continuity between point 1 and point 2. The discharge at point 1, we can express as u bar times the depth times the width. And this is going to be equal to u bar plus delta u bar times h plus delta h times the width b. Okay. And so the width appears on both sides, so we can divide out by the width. And what we end up with is u bar times h is equal to u bar plus delta u bar times h plus delta h. Okay. So let's go ahead and expand out this expression. If we expand out this expression, we get that U bar H is equal to U bar H plus U bar delta H plus delta U bar H plus delta U bar delta H. Okay, and this is where the term small gravity wave becomes important. For a small gravity wave, we are going to assume that the delta terms are very small, such that when you multiply them together, they become negligible. Okay, so we'll say that this term here goes to 0. So this is because this is a small gravity wave. Okay, so note now, since we removed this term here, U bar H and U bar H on this side, these two can cancel out. And what we end up with is that U bar delta H plus H delta U bar is equal to 0. Okay, so let's go ahead and save this equation. We're going to need it for later. I'll call this equation 1. Okay. Now let's go and apply the energy equation between the two sections as well. Okay, so applying the energy equation, on this side we have H and U bar. On this side we have H plus delta H and U plus U bar. Sorry, U plus delta U bar. This should be a bar as well. So let's go ahead and apply the energy equation and see what comes out. We have H plus U bar squared over 2G is equal to H plus delta H plus U plus delta U squared over 2G. Okay, we can expand out this term. What we end up with is H plus U bar squared over 2G. It's equal to H plus delta H plus, okay, let's expand out this term. We have U bar squared minus 2 delta U bar. Sorry, this should be plus delta U bar squared over 2G. And because it's a small gravity wave, this term here, which is delta U bar times delta U bar, is negligible. Okay, so this is again by the small gravity wave property. All right, and we can go ahead and we can rearrange this here. Let's go ahead and rearrange this equation. I see some of you are still writing, so I'll just wait a second here. And I promise this is going to pay off. This is going to be really cool. Here. So you got U squared plus, yeah. Yes. Okay. Okay, so let's go ahead and rearrange here. We have H minus H. Okay, so I've just moved H over to the other side. Is equal to delta H plus U bar squared minus U bar squared plus 2 delta U bar. And let me check that term there. Yeah, you're right. This should also have a U bar there. Okay. And if we simplify this, these two terms go away. And what we end up with is delta H plus 1 over G times U bar delta U bar is equal to 0. So this, we will also save this equation. So yeah, these two cancel out, and then this 2 goes away there. Okay, so this is, let's call this equation 2. This is from the energy equation. Okay, so we have continuity in the energy equation. Let's go back to equation 1. I promise you this is going to be really cool. This is going to blow your mind when I'm done with this. Okay, so from equation 1, we can rearrange this to isolate delta U bar. Okay, so from 1, we have that delta U bar, we can rearrange it to get, actually, let me just write the whole thing out. Yeah, from 1, U bar delta H plus H delta U bar is equal to 0. We can rearrange this for delta U bar is equal to negative U bar delta H over H. And let's go ahead and substitute this in to equation 2. Okay. And I think I'm not going to get to discharge control structures today, but that's okay. Let's go ahead and substitute this expression into 2. What we end up with is delta H plus 1 over G times U bar delta U bar is equal to 0. Okay. Substituting in that expression for delta U bar, we get delta H minus U bar squared times delta H over GH is equal to 0. And if we divide by delta H, we get 1 minus U bar squared over GH is equal to 0. Okay, let's rearrange this. We rearrange this, we can put U squared on the left side. So we get U bar squared is equal to GH. And finally, let's just take the square root of both sides. And what we end up with is that U bar is equal to delta GH. Okay, so what does this mean? What is U bar? What is U bar again? The speed of the water, but the water is actually still. So what is U bar actually? The speed of the wave. This is the speed of a small gravity wave. So if you have water, okay, it could be still or it could be moving, and you have some kind of disturbance occurring in water. Maybe someone throws a pebble into the water, maybe a drain opens up underneath the water and it causes a disturbance in the surface, maybe a fish jumps out of the water or whatever. Any wave that occurs in that water body will travel at the speed square root of GH. Okay, so that is the speed of a small gravity wave caused by a disturbance. Okay. So let's go back now and let's take a look at the, oh yes. No, this applies for either still water or moving water. So we just made it still to simplify this derivation, but it will work either way. No, it doesn't matter. You can just change your frame of reference to move with the wave the other direction. I think I saw a question down here.
How small is a small gravity wave?
So this is just it's a approximation. So note that if we carried this out and we left the delta terms, you could still carry out this derivation. It would just look a lot more messy. But essentially most real world kind of waves that you might see due to a disturbance will behave like this. Okay. Was there a question here?
would it still be the like the speed of the wave, or would that be like the difference between the like speed of the water?
Yes, so yeah, it depends what your frame of reference is, but if you are looking at kind of the speed of a wave moving through water, you do need to account for both velocities when you're looking at its absolute position over time. Yeah, which I'll show you in a picture in a second. Okay, are there any other questions? Okay, so we've derived the speed of a small gravity wave. We know that a wave will move with approximately the speed square root of GH. Let's go back and look at critical flow in a rectangular channel. What characterizes critical flow again? How can we express that mathematically? How can we determine whether it's critical mathematically? Right, we set the Freud number to 1. Okay, so let's say that the Freud number is equal to 1. Okay, and for a rectangular channel, let's just write it out. We have U times square root of the top width over square root of G times A. Okay, so for a rectangular channel, this will be U times square root of the bottom width over square root of G times B times the critical depth, right? And we can simplify this out, B divided by B, and we get U over root GH. Okay. So if we multiply through by root GH, we have that for critical flow, the velocity of the water moves at the speed root GH, okay, which is the same as the speed of a disturbance wave in the water. Okay. So critical depth, you can kind of think of it intuitively as critical flow as being when the velocity of the water moves at the exact same speed as the speed of a disturbance wave in the water. So this is the, let me just make a note, this is the velocity at critical flow. Okay, which means that we can actually determine if flow is critical or not just by looking at it. How might we do that? Throw something in it, exactly. So let's go through the different cases of what it might look like if we throw something in the water, okay? Let's go through the different cases. Let's say we have a body of still water and we throw a pebble into it. Okay, so let's take a look at the case of still water first. We have water that's absolutely still. We throw a pebble into it. And what we'll get is the following wave pattern. Okay, so if we throw the rock in and it hits right in the center here, it causes this ripple. And the ripple will move outward equally in all directions, right? And I'm going to roll drawing these circles here. Okay. Wow. Yeah, that was great. Okay. So if we throw a pebble into the still water, right, it lands at this X position here. And the ripples will move out equally in all directions, right? So you'll get this kind of symmetric looking pattern of ripples as they move through the water. Okay. So let's take a look at the case of critical flow. Okay, so we take a rock, we throw it into the water, and it creates this first ripple here. What is it that characterizes critical flow again? So how does the wave speed and the speed of flow, how do they relate for critical flow? Okay, they're the same. So what will the ripple pattern look like for critical flow if the wave is moving at the same speed as the water itself? Exactly. So the ripple the left, let's just say the water is moving this way. The left edge of the ripple will stay fixed in place. And you will get a pattern that looks like this. Okay, so you'll have the ripple moving out, but the ripple, the left edge of the ripple stays in place, and the ripple moves out to the right. Note that these should be circles. Actually, let me just draw it over again because they kind of look like ovals here, but these should all be circles. Okay. Note that the left edge stays in place because the wave speed is exactly equal to the velocity of the water itself. Okay. So what about the case of subcritical flow? What about the case of subcritical flow? Let's say we take our pebble and we throw it in the water. What will the waves look like in this case? Well, here's a question. Will they be able to move upstream? Yeah, so they will be able to move upstream, but just a little bit. So you'll end up with kind of these off-center circles where the wave is mostly moving to the right, but the wave can still travel upstream. Okay, so subcritical flow occurs when the wave speed is still faster than the water itself, and thus waves are able to propagate upstream. Okay, so under subcritical flow or under still water, the waves caused by a disturbance downstream can propagate upstream. What about for supercritical flow? What will the waves look like here? Let's take our rock and throw it in the water. So one, will waves be able to move upstream? No, they won't be able to because the water itself is moving faster than the wave can travel. And unlike critical flow, the water is moving faster than the wave. So the entire ripple will be translated downstream. Okay, so you'll end up with something that looks like this. Okay, so under supercritical flow, the entire wave moves downstream. Okay, and this has important implications for hydraulic design. This is going to come up again when we talk about culvert design in particular, because the flow regime upstream determines, whether or not we can control that flow occurring upstream, right? If it's supercritical, any changes we make downstream, any disturbance we create downstream, for instance, through a gate or through adding a control structure, the changes won't be affected upstream. Keep this in mind when we're going forward. This, I think, is probably the most intuitive way to think about critical, supercritical, and subcritical flow. Okay, and with that, I will see you on Thursday.